Hey everyone. In our last video, remember that we reviewed some of the classes of constitutional and stereoisomers. Remember that constitutional isomers are compounds that have the same molecular formula, but they differ in their connectivity of atoms. Stereoisomers, in contrast, they have the same molecular formula, and they differ not in their connectivity, but in the three-dimensional orientation of different groups. The types of stereoisomers that we had seen previously included cis and trans isomers. So we could see those on substituted cycloalkanes, and then I showed you how we could see them on alkenes as well. And then we learned about a new type of stereoisomers which involved chiral molecules. Remember that chiral molecules are molecules that are different from their mirror image, and the two mirror images, as long as they are non-superimposable or are different, are called enantiomers. Enantiomers arise from the presence of asymmetric centers or chiral centers, and chiral centers are carbons with four different groups or substituents attached. Alright, so what we're going to do today is we're going to go on and learn a naming system so we can differentiate between the two different enantiomers. And this system involves labeling different chiral centers as either R or S. So before we get into that, let's just see how we might look at a complex molecule and then just identify chiral centers. So here's two molecules. Cholesterol, right? We've all heard of cholesterol is in our blood. It's produced by our bodies, and it's important in the cell membranes of our body. Right? If we get too much cholesterol, then it can cause problems, plaques in our arteries, and high blood pressure, and things like that. Laulimalide over here is a compound that is produced by a marine sponge, and it has some very interesting anti-cancer activities. So what we're going to do here is we're going to look through and try to find chiral centers or asymmetric centers. And remember, again, they need to have four different groups, right? And to be different, they just have to be different in any way. To be the same, they have to be completely the same, all the way out to the end of a chain, atom after atom. They have to be different. All right, so let's look at cholesterol, and let's start over here on the left side. Right, so if we look at one of these carbons in this skeletal structure, what we want to do to determine whether there's a chiral center is figure out if there's four different groups, right? So in this case, we know that this has two hydrogens here, so if it has two of the same groups, then this can't be a chiral center. Same thing here, right? It has a CH2, can't be a chiral center. What about this carbon here? All right, for that carbon, we know that it has a hydrogen, so it has an OH, it has a hydrogen. Those are obviously different from one another, but what we have to be able to determine is whether these two carbons of the ring are either the same or different. And if we look at them briefly, if we just say, oh, this is a CH2 and this is a CH2, we think those are the same. But what we do is if those are the same, we go to the next position. Okay, so this next position on this side has two carbons attached, but it has a double bond to it. If we go the other way, this one's a CH2, and so these two sides are different, making this a chiral center. All right, if we keep going, then we have a CH2. That can't be. What about this position here? Well, whenever we have a double bond, it means that this carbon is only attached to 3 carbons, so there's no way that it can have 4 different groups. So a carbon, for it to be a chiral center, it has to be sp3 hybridized. It has to have 4 single bonds attached to it. Alright, so what about this position? Alright, so this has carbons attached all the way around, but are they different from one another, or are they the same? So we see this is a CH3, a CH2, a carbon with a double bond, and a carbon with 2 other carbons and a hydrogen. So all of those are different from one another. So this is a chiral center. If we keep moving over here, this one, right, has a CH2, has a CH, and a quaternary carbon. All of those are different, and a H. All of those are different. So this is a chiral center. This one, what do you think? Yes, this is a chiral center. This is a chiral center. This is a chiral center. This one is. This one is. All these other ones I'm not labeling have 2 H's, right? CH2, 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 CH2. What about this position? Is this a chiral center? Well, no, it has 2 CH3 groups, so those are both the same, so that's not a chiral center. Alright, so cholesterol has 1, 2, 3, 4, 5, 6, 7, 8 chiral centers. Alright, so if we drew this whole molecule out designating the chirality of each of those positions, then we could have a mirror image, and that mirror image would be different. So cholesterol would have an enantiomer, and cholesterol is a chiral molecule. Alright, so let's do the same process over here at laulimalide. So let's start over here. So what about this carbon? Now it's got a double bond, it can't be chiral. Same as these two. There's a CH2, so 2 H's, those are the same. What about this position? Okay, well it has an H. It has a CH2 that then goes on to a double bond, and a CH2 that continues around the ring. Those are different. And it has an H. So this is a chiral center. If we work our way around, we have CH2, CH2, CH2. Those can't be. This is a chiral center. This is a chiral center. All right, this is a CH2, CH2. This one can't. It has a double bond. CH2. This is a chiral center. This one is. This one is. This one is. This one. Double bond, can't be. This one is. And the rest either have double bonds, or they're CH2s or CH3s. So laulimalide has 1, 2, 3, 4, 5, 6, 7, 8, 9 chiral centers. So likewise, laulimalide has no symmetry to it. It would be different from its mirror image if we showed the chirality each of those centers, and so it would have a mirror image that's different from itself. Alright, so let's go back to a more simple situation and come up with a way to determine or to describe a single chiral center. Alright, so here's 2 models. These are supposed to be drawings that they're like the model kit that I showed you before. So in this one, probably the green is probably chlorine, the red would probably be either oxygen, but oxygen would have to have another bond, so let's say that this is bromine. Right, so this would be 1 bromo, 1 chloroethane. Alright, so because this carbon right here has 4 different groups, it has an H, it has a methyl group, it has a chlorine, and it has a bromine, so 4 different groups. This is a chiral or asymmetric center. All right? The structure on the right, how is it related to the one on the left? Well, those two are, in fact, if we made a mirror right here, these two are mirror images. Okay, what do you think? Are those two compounds the same, or are they different from one another? Well, those two are different, right? Because if we took this molecule right here, and if we rotated it around, the methyl group would swing around to this side, but the chlorine that's in front here would move to the back, and the bromine that's in back would move to the front, and so the bromine and the chlorine would be opposite of each other. So these are different from each other, so what do we call them? What's the relationship here? Okay, the relationship is that these are enantiomers. So they are stereoisomers of one another, and they are mirror images. Those two compounds have the same connectivity, right? They're going to have the same name, right? We would name them both as 1 bromo, 1 chloro. So let's just write up here, 1, oops, I did that wrong, right? Have a hyphen, 1 bromo, 1 chloroethane. Each one would have the same name, but we know that they're different from one another, so we have to have a naming system that distinguishes one from the other. All right, so this is where this RS nomenclature is going to come in. All right, so here's the strategy. First thing we have to do is identify the chiral center. All right, so we know how to do that already. We just did it on those complicated molecules in the last slide. Right, so we know that in this molecule it has 1 chiral center where the bromine and the chlorine are attached. Okay, so the next step, once we know there is one, is to rank the substituents around the asymmetric center. And we're going to rank them into 1 to 4, and where 1 is going to be the highest ranking. Okay, the ranking system that we're going to use depends primarily upon atomic number. All right, so its position in the periodic table. So it doesn't matter about size or length of carbon chain or anything. It's just the atomic number of the atom. Okay, so let's look at this molecule and see if we can rank the 4 groups attached. All right, so which of those, H, bromine, chlorine, or carbon, has the highest atomic number? Okay, well that would be bromine, right? Because bromine is below all of the other atoms. So then would come chlorine. Next would be carbon. And number 4, lowest priority, would be hydrogen. Okay? So we've ranked them all. We haven't had a tie or anything, and so what we're going to do is we now have to position this molecule so the lowest priority, the number 4, is pointing away from us. So we want to redraw the molecule so number 4 is pointing away. We could either look at it directly so the 4 is pointing straight away, or at least what we need to do is put number 4 in the position where it has a dashed line, because we know that's pointing back into the plane of the drawing. Okay, so what I'm going to do here in order to do that is I'm going to take this molecule and I'm going to rotate it around this carbon-chlorine bond. And what that's going to do, we're going to twist it like a propeller, is it's going to move the H down where the bromine is. The bromine is going to rotate over to where the carbon is, and the carbon's going to rotate up where the H is. Okay, so we're going to rotate this, we're going to keep the chlorine where it was. Okay? So up on top, the CH3, the methyl group, rotated up on top. The H rotated to the dashed line. The bromine rotated over to the left. So now we have it oriented with the lowest priority facing away. Let's just write our priorities again. Right? So this was 1, chlorine was 2, carbon was 3, and 4 was the lowly hydrogen. All right, so we've done that. So now the next step is we're going to draw some arrows, and the arrows are going to go from 1 to 2, 2 to 3, and 3 goes back to 1. So 1 is going to go to 2, 2 goes to 3, and 3 goes to 1. All right? So then here's the rules here. So if this circle is going clockwise, then we call it R. All right? Clockwise would be, just think about if you have the grab a hold of the steering wheel on this circle here, and if you rotate it to the right, you'd be turning your car to the right, so that's R. But this one's going counterclockwise, and so this one is called S. All right, S stands for sinister. It is Latin. All right, so this chiral center here would be S. All right, when we make the enantiomer, when we go to the opposite enantiomer, it's going to have the opposite chirality. So this one automatically is going to be R. So anytime we switch two groups on a chiral center, so for example here what we've done is we say take the chlorine and the bromine and we take them off and we switch places. Then we get the enantiomer. Alright? If there's more than one chiral center, we'll see later we'd have to switch each of the carbons. So let's just prove to ourselves that this would work like this. So let's do the same process that we did before. I'm going to rotate this around the chlorine. So I could do it in various ways, but this is just the way I've chosen here to get the number 4 in the back. Alright, so we're going to rotate number 4, the H, down to this position. Chlorine is going to stay in the same position because we're rotating around that bond. Okay, the CH3 rotates up on top, and the bromine rotates over to here. Alright, so let's write out our rankings again. So let's see, bromine was 1, chlorine is 2, methyl group is 3, H is 4. So now let's draw our arrows. We go from 1 to 2, 2 to 3, and 3 back to 1. Notice that our arrows are now going clockwise, and so this one is in fact R. This one over here was counterclockwise. Alright, so now what we would do for these names is that the structure on the left, we decided that was S, so this would be in parentheses S, 1 bromo, 1 chloroethane. This one over here, we'd put the R out in front, and then we'd have the same name. But this gives these two different names, and we know which enantiomer we were talking about. For examples. Alright, so first thing, what was the first step? First step is to identify whether there's a chiral center or not. Alright, so what about that left structure? Is there a chiral center? Yep, there sure is. There's one right here. Right? There's a OH, there's a CH3, there's a CH2, and then there's a carbon with a double bond. So we know that those four groups are different. So that one has a chiral center. So let's do our ranking. Okay, so in this case, we have three of the groups are just carbons, and one of them is an oxygen. Right? So the one with the oxygen has a higher atomic number, so it's coming first. Alright, so I'm going to show you another way to kind of bookkeep these rankings. So if we look at the CH3, what I'm going to do is in parentheses, I'm going to list the three atoms that are attached to that carbon, not including the one where we started. So we're always moving away from the chiral center. So this position, it has three hydrogens attached. So I'm going to list this as H, H, H. Okay, so for this one, they're all the same. Alright, for this carbon, right, we're not going to go backwards, so we go outwards, and we have one carbon attached, and we have two hydrogens. Okay, when we list them like this, we're going to always list them in order of decreasing atomic number. Carbon, hydrogen, hydrogen. Alright, so now we got to do this one over here, but we got a double bond. How do we treat that double bond? So what we do is we say that this carbon, because it has a double bond to this carbon, we treat it as though it's bonded to two separate carbons. Alright, so we treat that, it's going to equal, just for bookkeeping here, we'll draw out the carbon chain here, but this first carbon, right, it goes to one carbon, because it's double bond, we kind of take this double bond and we flip it out, and we draw another carbon out there. So this has another carbon. We're going to treat it like it's bonded to an extra carbon. Likewise, this carbon here, it has a double bond to that carbon, so we treat it as it's bonded to two carbons in this direction. So we put another carbon here. Right, and of course this has an H, it already did on the double bond, and this has another H here. So that's how we're going to treat these. So when we look at this carbon here, we're looking at this carbon, we see that it has two carbons, and a hydrogen. So we'll write this carbon, carbon, hydrogen. So now what we do is we compare these three atom lists. Okay, so we look at the first atom. Alright, so this one has a carbon, this one has an H, this one has a carbon. Alright, so CH3, these are all H's, so that's last. Okay, so in this case, notice that number 4 priority doesn't have to be a hydrogen like we saw before. In this case, the methyl group is number 4. Okay, so these other two are tied after the first group, the first atom. So we go to the second one, right? This one has an H at the second position. This one has a carbon, all right? So the tie is broken at this position. Okay, so the one on top, this is going to be number 2. This is going to be 3. Alright, so now we have to orient it. So number 4 is pointing away. Is that, do we have to rotate it or anything? No, if number 4 is the methyl. Notice it's already on a dashed line. So if number 4 is already pointing away. So now we go ahead and draw our circle. 1 to 2, 2 to 3, 3 back to 1. This is counterclockwise. So what is it? RS. It is S. Right? So that is an S chiral center. Alright, let's do one more here. Look at that one, it's got a lot more different groups attached. Alright, is there a chiral center? Sure is. There's one right here, right? Because all four of these groups are different. So let's rank it. Okay, which of those four groups is going to have the highest priority? Well, let's look. We look at the first atom. Oops, that's not what I wanted to do. Right, so don't just jump out here to the chlorine. We look at the first atom. Carbon, 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 oxygen. Alright, we know that oxygen has a higher atomic number than carbon. So the oxygen gets number 1. The other three groups are tied at this point. So let's do our ranking here. So this position has a double bond to oxygen, so we're going to treat it like it's bonded to 2 oxygens. So we're going to have, what comes first though, chlorine or oxygen? We put the higher atomic number first. So chlorine, oxygen, oxygen. Okay? So let's look at this one up here. What's attached to that carbon? This one just has 3 fluorines. And this position here has a double bond to carbon, so we count that for 2. And then has another carbon, so we treat this one as carbons, 3 carbons. Alright, so let's compare and rank these. So which one ranks the highest out of these? Alright, well, we just look at the first group. Chlorine, fluorine, carbon. Which one comes first? Alright, chlorine comes first, so this is going to be number 2. Fluorine comes next, number 3. And this ring here, that's called a benzene ring, is number 4. Alright, so again, look, we're lucky enough that number 4 is pointing away. And so again, we go from 1 to 2, 2 to 3, 3 back to 1, counterclockwise. Dang, I've made all of these have been S. Alright? So let me show you an interesting thing, or I think it's interesting at least. So this molecule on the right is it's called Mosher's. Well, it would be called Mosher's acyl chloride because that's this chlorine functional group. We'll learn that later, but it's used to determine the chirality of secondary alcohols. And the way that this works is we use it as a derivatizing agent. So we have an alcohol, and this R group over here would be a chiral group. Okay, so we do this reaction, the OH substitutes for the chlorine, gives off hydrochloric acid, and we form this molecule here. Okay, so everything else stays the same. Okay, we don't affect this chirality over here. And we get this molecule here. This is called an ester. Alright, and this type of ester, notice that now it has some chiral group over here that we can't see, and it has this chiral center right here. This, without going into detail right now, will allow us to determine the chirality of the group over here. Alright? So, in order to do this, we have to know what the chirality of the chiral center that we have drawn there is, though. So if we started out, what did we start out? We started out with S, so this one should automatically be S, right? Well, let's check it. Okay, so let's rank these groups again. Okay, so like before, oxygen's going to be ranked number 1. Okay, but what's going to be ranked number 2? Alright, so let's do what we did before. We know that this is 3 fluorines, right? This one is 3 carbons. But what about this one over here? Okay, this one, oh, it doesn't have the chlorine anymore, though, does it? It's a double bond of oxygen, so that's 2 oxygens. Now it has another oxygen, so it's like 3 oxygens. So what's going to come second? All right, in this case, now this is going to be second, right? Because fluorine has a higher atomic number than oxygen. This is going to be third, and this is going to be 4 over here again. All right, so let's do our rankings. We have 1 to 2, 2 to 3, 3 to 1, and look, this is now clockwise, meaning that this is now an R chiral center. So we haven't even done anything to this chirality right here, but it's gone from S to R. All right, so why? It's because in this reaction, we've done something that has changed the order of priorities. Okay? Most reactions, if we have S, it would go to S. But in this case, we've changed the priority of this group. It was second over here, and now it's third. We switched 2 groups, and so it went from S to R. All right? When I was first began as a faculty member, I was at the University of Hawaii. And one of my colleagues, who was really a pretty famous organic chemist, and they isolated a new compound from a marine organism, and they wanted to determine the chirality of some chiral secondary alcohol, so they used this method. However, they forgot that when they start with this compound, you buy this compound, and you do your derivatization, that the chirality of that center, the S goes to R, or if this was R, goes to S. And so if you get those backwards, you get exactly the backwards result. And so they made a mistake, published exactly the backwards result, and then had to correct it later. So I think that was kind of embarrassing for them. We wouldn't do that, right? Okay, so let me show you just a couple of shortcuts that we can do, right? So the trickiest part of this sometimes is that flipping the molecule over to be able to put the number 4 priority, the lowest priority group, in the back. So there's some ways that we can get around that. All right, so let's look at this first example. All right, so as we did this one before, right? There's a chiral center. Let's rank them again. So 1, 2, 3, 4. All right, so we have number 4 is directly in front. Okay, so it's directly in the backwards position where we want it to be. So if we just go ahead and do our arrows and do the rotation, 1 to 2, 2 to 3, 3 to 1, what are we going to get? We're going to get exactly the backwards result. So here we would say, okay, we're going counterclockwise. Okay, counterclockwise rotation usually gives us S, but then what we'd say is, no, this is actually R, because number 4 is in front. Okay, so we have it arranged exactly backwards, so we get just the backwards result. Okay, so you could use this type of analysis on an exam. You just have to make sure to explain what you're doing, right? Don't just set it up like this, rotate to the left or counterclockwise, and say, oh, this is R, because then I won't know if you really know what you're doing. Okay, so if you do it differently than the standard way that I taught you before, then make sure to explain it. Alright, so let's do one more example. Alright, so for this one, this is still not the best example for this really, but here's 1. Okay, oh yeah, it is. What's 2? Okay, 2 is going to be over here. 3 is the methyl group, and 4 is the H. Okay, so normally, and it wouldn't be that hard, what we did before is we just rotated the molecule. But let me show you a shortcut. So in this shortcut, what we do is we just switch places between the number 4 group and whatever's already in the back. Okay, so OH is in the back right here. We're going to switch these. Oops. Switch number 4 with group in the back. Okay, so then we're going to redraw this. Okay, so we have this isopropyl over here, carbon like this. Okay, we didn't do anything to the methyl group, that's still there. But we switched those groups, so now our H is in the back and the OH is pointing up. Alright, so now let's write out our rankings. OH was 1, isopropyl 2, methyl 3, H 4. Let's do our rotation. 1 to 2, 2 to 3, 3 back to 1, counterclockwise. Okay, we know that counterclockwise gives S, but what happens if we switch 2 groups? If we switch 2, we get exactly the backwards result. So this is not going to be it. This one is going to actually be R, because we switched 2 groups. Right? So if we switch those, we don't have to redraw it. We just, well, we did redraw it, but we don't have to rotate it. We're just switching those groups. But then we get the backwards result. So these are just different shortcuts that could be applied in different cases. Okay, the first shortcut might be good if we just happen to do it where we have number 4 coming in front, right? Then we don't have to redraw it. We can just rank them, do the rotation, and then take the backwards answer. This one over here is usually good where number 4 is not, it's in the plane of the paper, not in front or in back, right? Then we can switch those groups and then do the analysis and then switch it back. Alright, so those are just 2 shortcuts that you could use. But remember, if it's an exam, remember to explain what you're doing. Alright, so now what I'm going to do is I'm going to show you a different way of drawing chiral structures. Alright, I'm not particularly fond of this method, but it is used sometimes, particularly in biochemistry, and so you should know how to do it. I'm not going to actually test you on this, but I want you to be able to recognize what it represents. And these are called Fischer projections. They're oftentimes used for sugars, for carbohydrates, maybe for amino acids, but let's see how they work, and then I'll tell you why I don't really like them that much. Okay, so here's our molecule. We have this as 2-bromo, 2-bromo-butane. Okay, it has a chiral center. What's the chirality of that center? All right, if we're going to rank them, it would be 1, 2, 3, 4. Right, 4 is in front. So if we do our rotation, we go 1 to 2, 2 to 3, 3 to 1, counterclockwise. all right, which would usually give us S, but that's not going to be right. It's going to be R because number 4 is in front. All right, so this is R2-bromobutane. Okay, so we've got these drawings here, and I'm gonna use those to kind of show you how we're gonna position the molecule for this kind of drawing. So the first step we do is we're just gonna rotate this molecule up on it so it's vertically oriented. Okay, so this methyl group over here just rotates up to the top. Okay, notice the bromine's in back here, just like the one up above. Okay, so then what we're going to do is we're going to take an axis like this, and I'm going to rotate this so we're going to be looking straight between the bromine and the hydrogen. Okay, so here's the methyl group at the top. Here's the carbon. We're looking straight between the bromine and the hydrogen, and then the chain just goes on down. Okay, so when we draw this for a Fisher projection, we're looking at this direction. Right, so let's look at our chiral center. So really we'd have a carbon here. Notice that this H would be coming forward. This bromine would be coming forward. The CH3 would be going back. And down here, really, we just have CH2, CH3. So we don't have to worry about those because they're not chiral center. All right, so this is the direction of a Fisher projection. And so this is going to equal, in a Fisher projection, all we do is draw a line like this. We could put H's here and here, and across like this H and bromine. Okay? So notice where they're crossed, there's carbons, right? But we're not showing any wedges or dashed lines. So what we have to remember is that the bonds going up and the bond going down are pointing back like this, wedged, and the horizontal bonds are both coming forward. Okay? So this would be a Fisher projection. Okay? The reason I don't really like it is because it doesn't represent what the structure looks like at all, right? And it's just an awkward position when we don't put any of the bonds within the plane of the paper. They're all either coming out or going back. Okay, so this would be R, right? This one's R. So how would we draw the S compound? Okay, so we could draw the S just by redrawing this. And of course, if we switch two groups, so we put the bromine over here, like this, we just switch those. This would be the S2-bromobutane. Okay, so that's how Fisher projections are. So let's look at one more example, but I see a mistake right in there. So this can't be a 2, right? It can't be a 3, it's a CH2. Okay, this is a compound called glyceraldehyde. All right, it's kind of the simplest of all the possible sugars. And so what I'd like us to do is be able to convert this Fisher projection back to a normal type of structure for us that has a wedge and a dashed line. And then we're going to determine whether this is R or S. So let's just redraw it with wedges and dashed lines like it would be drawn here. So remember the bond going up and the bond going down, CH2OH, are going back from the center carbon, and the ones out to the side are wedges. Alright, so now what I'm going to do is I'm going to rotate this so I can put two of the bonds from that chiral center into the plane of the board like we normally would. Alright, so we're going to take an axis like this, and I'm going to just tip this thing over. And then I'm going to still have my aldehyde here, but I'm going to go like this. Carbon, carbon, this is a CH2OH. Alright, so we're going to be essentially looking at it from the side over here. Alright, so when we tip it like that, the H is going to be back, and the OH is going to be forward. Alright, everybody see that? So this would put two bonds in the plane. You know, usually we draw horizontally with the carbon chain going horizontally, zigzagging, right? If we have all of those bonds being staggered as we go from one position to another. So let's figure out whether this is R or S. Okay, so the O would be number 1. What would be ranked number 2? This top carbon up here, remember, because this, we have a double bond to oxygen, we treat it like it's bonded to 2 oxygens. And it has an H. Right, this one down here has an O, but then it just has 2 H's. Right, and then obviously this is number 4. Alright, so when we compare these oxygen, oxygen, it's a tie. So we go to the next position, oxygen versus hydrogen, right? Oxygen's higher. And so this is 2, this is 3. We go 1 to 2, 2 to 3, 3 to 1. This is R. R, glyceraldehyde. Okay? And of course, if we wanted to do S, we could just switch the positions of that center carbon. Alright, so our last type of problem we're going to do has to do with taking a name and drawing the structure. Alright, so we're going to reverse the process here. Alright, so here's our name, R4-methyl-2-pentanol. Alright, so we're going to start out, how are we going to start out this? We're going to start out by looking over here, pentane, so we're going to draw a 5-carbon chain. 4, 5. Alright, at the 2 position is going to be an alcohol, right? And at the 4 position, it's going to be a methyl group. So we're going to just number this from left to right. We're just going to do it like this: 1, 2, 3, 4. Let's draw the methyl group first, right here. All right. So what do you think? When we draw that methyl group, do we have to worry about making it a wedge or a dashed line? Well, the only time we'd really have to is if there was any difference, but because this position has 2 methyl groups, right? It's not a chiral center, so we don't even have to worry about that one. But for the alcohol, over here, we could draw the OH with either a wedge or a dashed line, and those are going to be different chiralities. And we want the R. So there's only one chiral center, so the R has to go with that chiral center. So what I would do is I would first just draw it so it's easiest to analyze, just arbitrarily. So I'm going to draw it in front. And H like this. So then when I rank these 1, 2, 3, 4, I can easily figure out whether it's R or S because number 4 is already in back. So we're going to go 1 to 2, 2 to 3, 3 to 1, clockwise. This is R. Look, we lucked out. We just drew it perfectly the first try. So what if I did the rotation and it came up backwards, so it came up S? Okay, so then we would just have to switch 2 groups, right? So we just have to cross this one out or erase this and put the OH in back. That would be the S. All right, so let's do one more. So again, here's 3-pentanol. It's going to work out. Let's do it. Let's see. 2, 3, 4, 5. All right, so then what are we going to have? 2, 4. This one doesn't really make sense. Let's change this to 2,3-dimethyl 3-pentanol. All right, if I had it, the reason I'm doing this is because if I had 2 and 4 dimethyls, those two groups would be attached here, and then the OH would be in the middle. We just have an isopropyl on each side. That's not even a chiral center. All right, so let's do it this way. So 2, okay, so that's not a chiral center, so we don't have to worry about it. But 3, we have methyl and pentanol, so we're going to have an OH. Let's just arbitrarily, I'm going to put the OH in front, and then the methyl group in back. Okay? So let's see whether we lucked out and got it correct or not. So this would be 1, this would be 2, this would be 3, methyl group is 4. So we just arbitrarily drew it so number 4 is in back, right? So 1 to 2, 2 to 3, 3 to 4, is this S? No, this would be R. Okay, so that's wrong. So we're going to just redraw this with the methyl group in front and the OH in back. Okay, so now this one would be S. Okay, so this is our correct structure over here. Okay, so one thing that I haven't shown you, which I probably should have, is let's just rank a couple of different groups. Okay, let me just make something up here. Okay, I'm just going to put an H here, make it easy. Carbon, and I'm going to put this, the bromine, and I'm going to put isopropyl there, and over here I'm going to put an OH. Okay, so let's rank these. Okay, so what's going to be ranked number 1? Okay, so remember, we go to the first atom. So we got O, carbon, carbon, H. Right, so we can rank 2 of these from that. We can go 1 here, 4 over here. All right, so which ranks next? Isopropyl or this one with bromine? Okay, so this is where some of you are going to make a mistake. Okay, you're just going to look straight out here to bromine and you're going to go, that thing has a higher atomic number, that has to be ranked higher. But you're going to get it wrong when you do that, because the key thing here is that we have to take it 1 atom at a time. Okay, so we come to each first atom and we go carbon, carbon, tie. All right? Then from there we just analyze it 1 position at a time. So this position has a carbon, those are for the 2 methyl groups, and a hydrogen attached. And this position has what? A carbon, hydrogen, and a hydrogen attached. So look at that. We go carbon, carbon and carbon, tie. We go to the next position, carbon, hydrogen. Look at that. This is going to be number 2 over here. This is 3 over here. All right, so we rank these even before we got out to the bromine. So it's critical that you take these chains one atom at a time. If we go out to the first atom, it's a tie. Go to the next atoms. If it's a tie, we keep going until they're either completely the same to the very end, or we find a difference. Okay? We don't just jump out further out on one branch too soon. Okay, one atom at a time. All right, so in this lecture, what we've done is we reminded ourselves how to identify chiral centers, or we practiced that. Remember, chiral centers or asymmetric centers have to have 4 different groups attached. They can't have a pi bond. They have to have 4 single bonds. And once we've identified a chiral center, we've learned how to classify them as either R or S.